Today we're going to be talking about characteristics of exponential functions, practice some graphing, and describing transformations. All of this will help us prepare for our quiz on Friday. The first example we're going to work on is p of x equals 2 to the x plus 1. I'm going to demonstrate graphing this function using the parent function and transformations. The parent function of p of x equals 2 to the x plus 1 will be y equals 2 to the x. The base for this function is 2, so this will be a growth function, and the table will be created by using the powers of 2. 2 to the 0 equals 1, 2 to the first power is 2, and 2 squared is 4. To fill in the negative side, we'll use the reciprocal of 2 to the first, which is 1/2, and the reciprocal of 2 to the fourth, which is 1/4. This will be the basic pattern that I plot on my graph. However, first I need to identify the transformations on my function, and in this case, there's one transformation, and that is a horizontal shift to the left 1 unit. There is no vertical shift, so there's no number added to the end of my equation right here. So my asymptote will be y equals 0. I'll go ahead and write that down over here. And I'll go ahead and plot that on my graph as well. So my asymptote will be here at y equals 0. So the graph will go flat on this line. Now I have a vertical shift, so that means I'm going to shift the entire graph to the left 1 unit. And I'm going to go ahead and draw my vertical shift line as well. So when I plot my graph, I'm going to start counting from the point where the horizontal and vertical shift lines intersect. So now I'm ready to plot my function. I'll start counting from here where the two lines intersect, and I'll plot this basic pattern of the parent function. Now these are not the actual ordered pairs of the graph, this is just the pattern that's created by the parent function y equals 2 to the x. So I'm going to get rid of this point so that we're not confused about the fact that that's not on our, actually on our graph, and I'm going to start plotting my function. So from this point, I'm going to count to the left 2 and up 1/4 of a square. I'm going to go back to that starting point and I'm going to count to the left 1 and up 1/2. From here up 1. From here to the right 1 and up 2. And then back to here to the right 2 and up 1, 2, 3, 4. Now more points could fit on our graph as well, so if I wanted to do 3, 2 to the third is 8, we'll go ahead and plot that one as well. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So there are the points on my graph. This end is flat to the asymptote, and this end is going up. Now we're ready to talk about the characteristics of the function. The domain of this function is going to be negative infinity to positive infinity, as is true for all exponential functions. The range, remember we described range from bottom to top. The bottom of this function flattens out at y equals 0. So the start or bottom of the range will be 0. And then the top of this function goes to positive infinity because it's pointing up. Next, we'll discuss the y-intercept. The y-intercept is the point where the graph crosses the y-axis. That's right here at 0, 2. Don't be tempted to choose the point in your table because we made our table from the parent function and not from the actual points that are on our graph. If you want to create a table straight from your function in your graphing calculator, you may do that. You don't have to graph by transformations. I was just demonstrating that as a shortcut. Either way works the same. This graph is increasing over the entire function from left to right, starting low and then ending high. So the interval of increase is negative infinity to positive infinity, representing the entire graph, and there is no interval of decrease. The end behavior as x approaches negative infinity on the x-axis is on the left. On the left side of this graph, it's getting close to the asymptote, so the y value will be 0 here. And remember, we're describing what the y values are doing as we approach the left side of the x-axis. As we approach the right side of the x-axis where positive infinity exists, the y values are going up to positive infinity. This should match this. Finally, positive and negative intervals. Remember that the positive interval is the part of the graph that exists above the x-axis, and this entire graph is above the x-axis. So the positive interval will be negative infinity to positive infinity, and then the negative interval will be none, because no part of the graph lies in this area below the x-axis. Then we'll find the average rate of change. The average rate of change, the interval we've been given, is 0. So the point on the graph where the x value is 0 is this point here at 0, 2. And then the other point we're using is 2. So 1, 2, 8. If you didn't plot 2, 8, like we had to extend our table to get this point onto our graph, you could substitute 2 back into your equation to find the y-coordinate that goes with it. Since we have this on our graph, I'm just going to count the slope, rise over run. So that's 1, 2, 3, 4, 5, 6 over 2, which is 3. So the rate of change for this function over the interval from 0 to 2 is 3. Now we're ready to move on to the next example. This function also uses the basic parent function y equals 2 to the x, but this one has a vertical shift down 2 units. This will cause our asymptote to move down to y equals -2. I'll go ahead and put that on my graph. We have no horizontal shift, so we'll be counting our graph starting at the y-axis and the point where the y-axis intercepts our asymptote. I'm going to complete the table for my parent function. 2 to the 0 is 1. 2 squared is 2. Let's get rid of that. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. And we'll go ahead and put 2 to the third, which is 8. And then we'll go in the opposite direction. So this will give us the reciprocal. 2 to the -1 is 1/2. And 2 to the -2 is 1/4. Now we're ready to plot those. And again, we're counting from where the y-axis intercepts our asymptote. So from this center, we're going to go to the left 2 units and up 1/4, to the left 1 unit and up 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. Our graph will be close to the asymptote on this end, and then go up on the right. Again, we plotted the pattern for our parent function, but you could type this into your graphing calculator and create a table, or create a table by evaluating the function and get the exact ordered pairs that lie on the graph. But just for point of reference, this point here, the coordinates are 2, 2. 2, 2 does not appear in this table because this table represents the parent function and not the function represented by our transformed equation. The domain of this function is -infinity to positive infinity, just like all of our exponential functions. And the range, bottom to top, The bottom is at y equals -2, same as our asymptote. And the top, if I follow it, it goes up on the right-hand side. Top is positive infinity. The y-intercept is 0, -1. The interval of increase, this entire graph is increasing from left to right, so it'll be -infinity to positive infinity, and there is no interval of decrease. Now we'll describe the end behavior. As x approaches -infinity, that's the left-hand side of our graph. The negative infinity side of the graph approaches the asymptote at -2. As x approaches positive infinity on the right, the y values are going up to positive infinity. Now we'll talk about the positive and negative intervals of our graph. The positive interval is the part of the graph measured on the x-axis where the graph is above the x-axis in the positive zone. So the function itself crosses the x-axis at x equals 1. And this graph, this function, is above the x-axis everywhere to the right of that dividing line. So the interval that is positive will go from +1 to positive infinity. Now, the negative side of the graph is this side. This part of the graph is all below the x-axis, and that is from -infinity to that dividing line at +1. So our negative interval will be from -infinity to 1. Finally, we'll find our average rate of change. We're going to count the slope of the function on the graph from where x equals -2, so we'll go to -2, here's my point where x equals -2 on my graph, to +1, which is right here. So we'll count the slope, the rate of change. That's going to be the rise over run between those 2 points. That's up 2 and to the right 1, 2, 3. So our rate of change is 2/3. Now we're ready to move on to the next page.